So in today's video, we are going to focus on a balanced star delta three-phase system. So a balanced star delta system is a system which consists of a balanced star connected source feeding a balanced delta connected load. Now what this primarily means is that we have the source configured in star, and that is feeding the load, which is configured in delta. And in such a circuit, there is no neutral connection from the source to the load. So no neutral connection from the source to the load. So how do we approach such a circuit? Now we have a number of ways in solving such circuits. However, in this video, we are going to consider an alternative approach, that is to transform the delta connected load to an equivalent star connected load, so that after the transformation, we obtain a star-star system. That is, we have the source connected in star and also the load connected in star. And then we do that using the delta star transformation formula, giving us zy or z star equals z delta divided by 3. So after this transformation, the next thing we are going to do is to determine the three-phase current. That is by considering one phase and then calculating that phase current from the phase voltage and phase impedance the same way as in a single phase system or a single phase circuit. So you know, in a single phase circuit, we have the source voltage, in this case the phase voltage, connected across the phase impedance, and then we have current IP, which is the phase current flowing through the circuit. And then to find the phase current IP, that is giving us the phase voltage divided by the phase impedance. So this is how to find the phase current. And then if you want to find the line current, because we have a star connected load, the line current is equal to the phase current, and assuming that the line voltage is not given, then we can find the line voltage, which is equal to square root of 3 times the phase voltage. So having this in mind, let's solve a couple of examples. So for example 1, a star connected impedance Z1 equals 20 plus J37.75 ohms per phase is connected in parallel with a delta connected impedance Z2 equals 30 minus J159.3 ohms per phase for an impressed three-phase voltage of 398 volts line to line. A. Compute the line current, B. the power factor, and C. the power taken by the parallel combination. Let's try to solve this question together. So from the question, we are being given a star connected impedance, that is Z1 equals 20 plus J37.75 ohms per phase, and that is connected in parallel with Z2, that is a delta connected impedance, which is giving us 30 minus J159.3 ohms per phase. And then we have the line to line voltage or line voltage giving us VL equals 398 volts. So A, we are asked to find the line current. Now to find the line current, the first thing we are going to do is to transform Z2, which is delta connected impedance, to an equivalent star connected impedance, and then we do that by using the delta star transformation formula. So that is giving us Z2y equals Z2 divided by 3. Now we have Z2 to be 30 minus J159.3, and then we have that divided by 3. 30 divided by 3 is 10, and then 159.3 divided by 3 gives 53.1. So we have Z2y equals 10 minus J 53.1 ohms. So this is the equivalent star connected impedance per phase. Now the next thing we are going to do is to find the parallel combination of Z1 and then Z2y. Now we have Z1 and then Z2y, both star connected impedances. So let's find the parallel combination of the two. So that is giving us Z1 parallel Z2y. So that's going to be, we have Z1 times Z2y divided by Z1 plus Z2y. So we have Z1 20 plus J 37.75 times Z2y, which is 10 minus J 53.1 divided by 20 plus J 37.75 plus 10 minus J 53.1. And then when you compute this, you are going to get 67.490 plus J 11.716 ohms. So this is the parallel combination of Z1 and then Z2y. Now converting this from the rectangular form to the polar form, you have 68.499 polar, 9.848. Now let's try to represent this in the circuit form. So we have the phase voltage, and that is connected across two impedances. We have this to be Z1, and then we have this to be Z2y. So that is why we found the parallel combination of these two impedances. So that is 68.499 polar, 9.848. So to find the phase current IP is giving us the phase voltage divided by the parallel combination of this impedance. So that is Z1 parallel Z2y. So we have the phase voltage. Now because we have the source to be star configured, it means that the line voltage is equal to square root of 3 times the phase voltage. Therefore the phase voltage is giving us VL divided by root 3. Now we have the line voltage given in the question to be 398 volts. So we have 398 divided by root 3 and that is equal to 229.79 volts. So this is the phase voltage. So inserting this value here, we have 229.79 divided by 68.499 polar 9.848. So dividing these two values, that is 229.79 divided by 68.499, that gives 3.355 polar. 0 minus this value gives the negative of this, so we have negative 9.848. So this is the value of the phase current. Now, because we have a star connected load, we know that the phase current is equal to the line current. Therefore, we have the line current to be 3.355 polar negative 9.848 amperes. Now let's move on to B. So for B, we are asked to find the power factor. Now focusing on the parallel combination of the impedance, we had the impedance to be 68.499 polar 9.848. So we have this value to be the polar impedance, and then we have this value to be the phase angle. And to find the power factor is giving us cosine of the phase angle. So we have cosine of the angle 9.848, and cosine of this value gives 0.985. Now because the phase angle is positive, then it means that the power factor is going to be 0.985 lagging. Now to C, we are asked to find the power taken by the parallel combination. So the power in a three-phase system, that is the active power, is giving us square root of 3 times the line voltage times the line current times cosine of angle phi. So we have root 3 times the line voltage, which is given in the question to be 398, times the line current, which is 3.355, times cosine of angle phi, which is the power factor 0.985. And then when you multiply all these values, you are going to get 2,278 watts, and that can be simplified as 2.28 kilowatts. So now let's move on to the next example. Example 2. A manufacturing plant draws 415 kilovolt amperes from a 2400 volts three-phase line. If the plant's power factor is 0.875 lagging, calculate A, the impedance of the plant per phase, and then B, the phase angle between the phase voltage and phase current. So from the question, we are being told that a manufacturing plant draws 415 kilovolt amperes of power, which happens to be the apparent power. So that is 415 kilovolts amperes from a 2400 three-phase line. So this happens to be the line-to-line voltage, or better still, the line voltage, that is 2400 volts. and we can express this as 2.4 kilovolts. We also have the power factor of the plant to be 0.875. Now A, we are asked to find the impedance of the plant per phase. So the impedance per phase, which is given as ZP, is equal to the phase voltage divided by the phase current. So we first of all need to find the phase voltage as well as the phase current. Now in this type of question, we are not told the configuration of the plant. Now if that happens in the question, you should realize that you have a star configuration. So whenever the configuration is not mentioned, then we consider that to be a star configuration. Now in a star configuration, we know that the line voltage is given as square root of 3 times the phase voltage. So if you want to find the phase voltage, that is simply the line voltage divided by root 3. So let's find the phase voltage. So we have the line voltage 2400 divided by root 3, and that is equal to, we have 1385.64 volts. So this is the value of the phase voltage. Now since we have the phase voltage, let's try to find the phase current. Also in a star configuration, you realize that the line current is equal to the phase current. So if you should find the line current, then that will be equal to the phase current. Now from the apparent power, we know that S is given as square root of 3 times VL times IL. That is considering a 3-phase circuit. We have the value of the line voltage. We can find the line current, which is equal to the phase current. So the line current IL is given as the apparent power divided by square root of 3 times the line voltage. Now let's insert the values of S and then VL. So we have S to be 415,000 divided by square root of 3 times VL, which is 2400. And the result of this gives 99.83. So we have the line current, which is equal to the phase current, to be equal to 99.83 amperes. So now that we have the phase voltage and the phase current, we can find the impedance per phase. So that is given as 1385.64 divided by 99.83, and that is equal to 13.88. So that is the impedance of the plant per phase. Now let's move on to B, where we are going to find the phase angle between the phase voltage and the phase current. Now we know that the power factor is equal to cosine of angle phi, which is given in the question to be 0.875. So to find the phase angle, that is basically going to be cos inverse of 0.875, and that is going to be 28.96 which is approximately equal to 29 degrees. Therefore, the phase angle between the phase voltage and the phase current is equal to 29 degrees. Let's move on to the last example. Now to example 3. A star-connected motor is connected to a 4000 volts 3-phase 50 Hz line. The motor produces an output power of 2681 kilowatts at efficiency of 93% and a power factor of 0.9 lagging. Calculate A, the active power absorbed by the motor, B, the reactive power absorbed by the motor, C, the apparent power supplied by the transmission line, and then D, the motor line current. So from this question, we have the line voltage giving us 4000 volts. We have frequency 50 Hz. We have the motor producing an output power, that is the output active power 2681 kilowatts, and then we have efficiency 93%. Dividing this value by 100, you have 0.93. we have the power factor to be 0.9 lagging. So A, let's try to find the active power absorbed by the motor. Now the active power absorbed by the motor happens to be the input power. Now we know that efficiency is giving us the output power divided by the input power. So if you want to find the input power, then you basically interchange the positions of efficiency and the input power. So that is equal to the output power divided by efficiency. We have output power to be 2681 kilowatts divided by efficiency 0.93, and then we have our final answer for the power inputs, or better still, the active power absorbed by the motor, to be 2882.8 kilowatts. Now let's move on to B. We are asked to find the reactive power absorbed by the motor. Now, because of the information we have available, we can't straight away move on to find the reactive power. We first of all need to find the apparent power and then the reactive power. Now the real power, or the active power, is giving us the apparent power times cosine of angle phi. Now with this equation, we can find the apparent power. So with this, we have the apparent power being equal to the active power divided by cosine of angle phi. Now this power we are talking about happens to be the input power, or the active power absorbed by the motor. So we have S equals input power divided by cosine of angle phi. So we have the input power to be 2882.8 divided by cosine of angle phi is giving us the power factor, so 0.9, and then that gives 3203, so kilovolts amperes. Now let's move on to find the reactive power once we have the value of the apparent power and the active power. So from the power triangle, we know that S square is equal to P P square plus Q square. And then Q is equal to the square root of S square minus P square. So we have S to be the apparent power, which is 3203. So we have the square of it minus the square of the input power, that is 2882.8. And then when you simplify this, you are going to get 1395.9, and that is measured in volts amperes reactive. So this is the value of the reactive power. C, we are going to find, or we are asked to find, the apparent power. So the apparent power is 3203. So apparent power 3203 kilovolts amperes. And then D, we are asked to find the motor line current. The motor line current. Now for a three-phase system, the apparent power is given as square root of 3 times the line voltage times the line current. So from this equation, we can find the line current. So the line current is given as apparent power divided by root 3 times VL. We have S to be 3203 divided by root 3 times VL, which is given in the question to be 4000. Calculating this, we are going to get 462.3 amperes, and this happens to be the motor line current. So that's it for today's video. Thanks for watching, and see you in my next video. Bye bye.